You know, in category theory, we've got this incredibly powerful language for talking about systems. You have your objects and you have the relationships between them. But what happens when we turn that powerful language back onto itself? Today, we're diving into Chapter 12 of Saunders Maclean's classic, Categories for the Working Mathematician, to explore what it means to find structures inside of other categories. We're going to be adding new layers of abstraction to see complexity in a completely new way. Okay, so let's start with the big question, the one that really drives this whole field of study. We're pretty comfortable with the idea of arrows, or morphisms, right? They connect objects. But this question, this pushes us way further. It's asking, how do we formalize the connections between the arrows themselves? This is the exact puzzle that higher category theory is trying to solve. So to answer that question, we literally need to build a new layer of structure. I want you to think of it like we're climbing a ladder of abstraction. With every single rung we climb, we get a richer, more detailed way to describe the world. We're moving beyond that flat picture of just dots and arrows. And for this whole journey, this is our map. Maclean's Categories for the Working Mathematician. It's the book. It gives us the solid, foundational language we need to turn these kind of intuitive ideas about structure into real, rigorous mathematics. All right, let's start on the ground floor just to make sure we're all on the same page. At its very core, a category is beautiful and simple. You've got dots, which we call objects, and you've got arrows between them, which we call morphisms. That's it. This simple foundation is what we're about to build everything on top of. So, let's take our first step up that ladder. What if the objects in our category weren't just these abstract, featureless points? What if they had their own internal structure? This is the big idea of looking for categories that live inside of other categories. Okay, now this is where it starts to get really mind-bending and cool. Maclean makes this formal by having us imagine that our collection of objects isn't just a set, but is itself a single structured object. And the same thing for our arrows. So now, all the rules that make a category work, like composition, are happening inside this bigger, richer environment. To make that a little less abstract, just think about the category of groups, right? The objects are groups, and the arrows are group homomorphisms, maps that preserve that group structure. Well, an internal category in this world would be one where the collection of objects itself forms a group, and the collection of arrows forms another group. Every single part of the category is just soaked in that same algebraic structure. All right, let's climb to the next rung and see how this builds. We've given structure to the objects. So what's next? Well, now we're going to add structure between the arrows. This is where we directly tackle that big question we started with, and it adds a whole new dimension to our thinking. And boom, this comparison makes the leap crystal clear. A normal category, it has two levels of data, objects and arrows. A two category adds a third level, the two cell. So if you have two different arrows, let's call them F and G, and they're both going from object A to object B, a two cell is a map between F and G. It's an arrow between arrows. This quote just nails it, right? It perfectly captures the whole motivation. We're just applying the main idea of category theory one level up. A classic example here is the two category we call CAT. Its objects are categories, its arrows are functors, which are maps between categories, and its two cells are natural transformations, which are these structured ways of comparing those functors. So far, we've just been adding new layers of structure. But what if we could get even more power, not by adding something new, but by relaxing a fundamental rule? Let's take a look at what happens when the composition of arrows isn't strictly associative anymore. And this is the whole idea behind a bicategory. Instead of demanding that H composed with G composed with F is exactly equal to H composed with G composed with F, we just say, hey, as long as there's a natural isomorphism, a two cell that connects them, we're good. We're swapping out strict equality for structured comparison. Now, I know what you might be thinking. This seems kind of strange at first, right? Why would we want to weaken a core rule like associativity? Isn't that just making things messy and imprecise? Well, it turns out that this flexibility is absolutely crucial for modeling the way real, messy, complex systems actually behave. Okay, here's the payoff. When you're putting complex processes together, the order you do them in often matters. The results might not be identical, but they're very often equivalent or isomorphic. And that little bit of difference, that isomorphism, it isn't a bug, it's a feature. It actually represents an emergent property of the system. Bicategories give us the language to track these effects, to capture how things that aren't strictly equal can still be meaningfully compared. So we've climbed the ladder of abstraction. We figured out how to add structure inside of objects, between arrows, and even how to make that structure flexible. Let's take a second, look down from the top, and see what this new language really lets us do. This quote just gets to the absolute heart of it. We're not building all these complex abstractions to make things harder. We're doing it to find the underlying simplicity. The whole goal is to find the right perspective, the right structural language, where all the messiness of a phenomenon just melts away, and you're left with this elegant, simple principle that was hiding underneath all along. So let's just quickly recap our climb. Internal categories, they gave our objects depth. Two categories, they gave us a way to compare the relationships themselves. And bicategories, they gave us the flexibility to model how complex systems actually compose. And when you put it all together, what you get is this incredibly expressive language for describing the very nature of structure itself. And believe me, this isn't just some abstract mathematical fantasy. Think about functional programming, a recursive data structure, like a list. You can see that as an object. A function that processes that list, like a fold or a reducer, that's basically a morphism. Well, the relationships between all the different ways you could fold that list, that is captured perfectly by this higher categorical language. By climbing this ladder of abstraction, we've basically built a powerful new lens to see the hidden architecture of all kinds of complex systems, from computer science to physics. And it leaves us with this really tantalizing final question. Now that we have this language for describing structure itself, what tangled, complicated mess are we going to unravel and find the simplicity in next?